Ever catch a little dent on your car door and wonder if it's, a big deal?
Hmm.
Or maybe you're trying to figure out if a repair on something at home is really solid. That feeling of wondering about hidden weaknesses.
Yeah, I know that feeling.
Well, that's kind of where we're starting today.
And what's fascinating is how that everyday curiosity, it just takes on a whole new level of importance when we're talking about something like an airplane,
Yeah,
thousands of feet up.
exactly. Welcome to the deep dive. Today we're going to unpack the world of aircraft metal structural repair.
Yeah.
Now, forget those quick fixes you might do around the house. This is a realm where physics, cutting-edge material science, and incredibly skilled craftsmanship all meet.
It's pretty intense stuff.
Think about it.
Yeah.
Every tiny piece, from the smallest rivet to a carefully shaped panel, it plays a critical role. Up in the air, those seemingly insignificant imperfections, they can have major consequences.
And if we connect this to the bigger picture, what you'll discover is that the core ideas we'll be exploring, like understanding how forces act on structures, the properties of different materials, and the absolute necessity of precise techniques, they aren't just relevant to aircraft. They pop up everywhere.
Yeah.
Structural integrity matters.
So our roadmap for this deep dive is a document called Aircraft Metal Structural Repair. Now, this isn't exactly light reading. It's more like a technical Bible that lays out the gold standard for how these repairs should be done.
Mm-hmm. Very detailed.
It dives into everything from the massive stresses and aircraft experiences in flight, and on the ground, right down to the very specific tools and step-by-step methods that ensure every repair is safe and sound.
Which kind of brings up a crucial point for anyone listening.
Yeah.
How do you know if a repair is more than just cosmetic, if it's truly strong and reliable?
Exactly.
Our goal today is to take this technical treasure trove, sort of extract the most important insights, and give you a solid understanding of what it takes to keep metal aircraft, and really, in a broader sense, any important metal structure holding together safely.
But we promise to keep it engaging. No dry lectures here.
Definitely not.
Okay, so let's get into the fundamental challenge of repairing an aircraft. Aircraft design is all about being as light as possible, right?
Absolutely. Every extra pound impacts fuel efficiency, performance, everything.
So when you're making a repair, it's a real tightrope walk. You need to make it strong enough to do its job, but without adding unnecessary weight.
And what's really interesting, and maybe a bit counterintuitive, is that a repair that seems overly robust
Yeah.
can actually cause problems.
How so?
Well, the source points out that making one part too stiff can create what are called stress risers.
Ah.
Imagine reinforcing one spot so much that it becomes this rigid anchor in an otherwise flexible structure. What happens is it forces all the stress to concentrate right at that hard point.
Okay, see.
And that concentration can potentially lead to cracks starting in other, maybe weaker areas nearby.
So it's not just about making it strong, but making it compatibly strong.
Precisely. It's that perfect balance. Not too much, not too little, just right.
And to achieve that, you really need to understand what you're working with. And in modern aviation, the workhorse really is sheet metal, mostly aluminum alloys.
Yeah, the widespread use of sheet metal is pretty remarkable. As the source explains, these relatively thin panels, they do double duty.
Right.
They form the aircraft's main structure, and they act as its outer skin. And then these panels are joined together using rivets and other specialized fasteners.
And you see this everywhere, not just on huge passenger planes, but also on small single-engine aircraft.
Mm-hmm.
The source even mentions sheet metal being used in composite aircraft for things like instrument panels.
Right, so it's versatile.
Now, when we talk about how thick this sheet metal is, they use a term called gauge, and it works a bit backward from what you might expect, doesn't it?
It does. A higher gauge number, like say 30, actually means the metal is thinner,
Yeah.
while a lower gauge, maybe 8, indicates a thicker sheet.
So thinner is higher. Got it.
And this variety in thickness, it just reflects the different structural demands placed on different parts of the aircraft. Areas that take a lot of stress will use thicker gauges, naturally,
Makes sense.
while less critical components might use thinner ones to save weight.
Okay, now, a repair isn't just about covering up damage. It has to become part of the original structure, seamlessly handling all the forces it was designed for.
That's absolutely key. The source emphasizes that any repair must be able to accept, carry, and then smoothly transfer stresses back into the surrounding undamaged structure.
Like blending it back in.
Exactly. Think of these stresses as invisible forces flowing through the aircraft.
And that idea of stress flow is critical, isn't it?
Hugely critical. The source highlights that if there's a sudden change in the shape or thickness of a structural part, what engineers call an abrupt change in cross-sectional area,
Right.
it can create these stress concentrations. It's a bit like putting a kink in a garden hose. The pressure builds up right at that point.
Ah, good analogy.
And over time, these stress concentrations can lead to tiny cracks forming due to fatigue, and eventually, well, that can cause a structural failure.
And it doesn't take a massive impact to cause a problem, right? Even something small.
That's the scary part. Even something as seemingly minor as a scratch or a gouge on a piece of metal that's under a lot of stress can act as a point where stress concentrates.
Wow.
And that could potentially lead to that part failing down the line.
So what kind of these invisible forces are we actually talking about? The source breaks it down, I think, into 6 main types.
Yeah, basically 6 types of stress. These stresses arise from all the different loads an aircraft experiences, both on the ground and when it's flying. They can be grouped into basic stresses and then combination stresses.
Okay, let's start with the basics then. First up.
First, there's tension. Think of it as simply a pulling force.
Okay.
So source gives a great example. The engine is pulling the aircraft forward, while air resistance is trying to slow it down. That tug of war creates tension, trying to stretch the aircraft apart.
And they measure that strength, right? Tensile strength.
Yeah, tensile strength, usually in pounds per square inch, PSI. It's basically how much pulling force it can handle before it breaks.
And you mentioned something about net area.
Right. When figuring out how strong a part is under tension, you have to consider the net area. If there are holes in the material, like for rivets, those obviously reduce the amount of solid material that's actually resisting the pull. What's interesting is that the fasteners in those holes don't directly help resist the pull across the hole. It's the solid metal around the holes doing that work.
Got it. Okay, so tension is pulling. What's next?
Next is compression, which is simply the opposite. It's a pushing force.
Like the weight on the landing gear.
Exactly. Think about the weight of the aircraft pressing down on the landing gear when it's on the ground. That's compression. It tries to squeeze or shorten the material.
And its strength is compressive strength. Makes sense.
Yep. Then we have shear stress.
Shear. Okay, what's that like?
Imagine it as a force trying to make one layer of material slide past another. The source uses the example of 2 metal plates joined by rivets being pulled apart.
Ah, okay.
That pulling force is trying to shear, or basically cut, the rivets right through the middle.
So shear strength is key for fasteners then?
Very key, especially in designing joints. The source notes that a material's shear strength is usually about the same or maybe a little less than its ability to handle tension or compression.
Okay. And there's one more basic one. Bearing stress.
Bearing stress, right. This is the force that the rivet or bolt itself exerts on the inside edge of the hole it's sitting in.
Ah, the pressure between the fastener and the whole material.
Exactly, it's the pressure there. Ideally, when designing a joint, you want the total shear strength of the rivets to be roughly the same as the bearing strength of the sheet material.
Why is that?
Well, you don't want the rivet to fail before the hole gets damaged, or vice versa. You want the whole joint to be balanced in its strength. Makes it more reliable.
Right, makes sense. Okay, those are the basic ones. Then you mentioned combination stresses.
Yes, where you have more than one basic stress acting at the same time. First is bending. Think about an aircraft wing in flight.
Lift pushing up, weight pushing down.
Exactly. Lift tries to push it up, while the weight of the plane and other forces push down. That creates a bending force. And bending stress is actually a mix of tension and compression.
Oh, so?
Well, when something bends, one side gets stretched, that's tension,
Okay.
while the opposite side gets squeezed, which is compression.
Ah, clever. Okay, bending, and the last one.
Torsion, which is basically a twisting stress.
Twisting, like wringing out a cloth.
That's a great visual, yeah. The source gives the example of the engine trying to twist the aircraft as it propels it forward, but other parts resist that twisting. Torsion creates shear stresses within the material as one part tries to rotate past another.
Okay, tension, compression, shear, bearing, bending, torsion. Got it. So understanding which of these are acting on a damaged area is pretty fundamental to repairing it correctly. Absolutely fundamental.
Now let's talk tools. Before you even think about bending or joining, you need incredible precision in measuring and marking, right? Layout tools.
Precision is absolutely paramount. You can't afford mistakes here. The source details a variety of layout tools, starting with the basics. Scales, essentially your rulers.
Different lengths, fractions, decimals.
Exactly. And a little pro tip the source mentions for accuracy. Start measuring from the 1-inch mark, not the very end, as the tip can get worn down.
Good tip. Then there's the combination square. Sounds fancy.
It's a really handy multi-tool. It's not just a ruler. It has adjustable heads, a stock head for 90 and 45-degree angles, a protractor head for any angle, and even a center head for finding the middle of round stuff easily.
Wow, quite versatile.
Very. Then you have dividers, look like a compass, but with 2 sharp points, used for setting and transferring precise distances. And a rivet spacer is a neat tool for marking out consistent, even spacing for rivets. Saves a lot of measuring.
Okay, and for actually marking the lines on the metal. You typically use a scribe. It's very sharp, leaves a fine scratch line. Then, to make small indentations as reference points for drilling, you use a prick punch.
Little tiny marks.
Right. And those tiny marks are then enlarged with a center punch. That helps guide the drill bit and stops it from wandering when you start drilling.
Prevents slipping.
Exactly. The source even mentions an automatic center punch spring-loaded, so you just push down, no hammer needed.
Nice. What about transferring hole locations, like from an old part?
That's where a transfer punch comes in. Clever tool.
Yeah.
You align it with the existing hole on the template or old part, give it a light tap, and boom, location marked.
Simple but effective. And a drive punch.
Drive punch has a flat end. It's used for carefully pushing out damaged rivets, pins, bolts, that kind of thing.
Okay. And for bigger holes, like for instruments.
That's where a chassis punch is used.
Yeah.
They come in specific sizes, usually in 116th-inch increments, for making those larger, clean holes.
And I think the source mentioned an awl.
Yep, the awl. Another pointed tool used for marking, but also handy for aligning existing holes sometimes, like when installing deesser boots. And the hole duplicator is another one for accurately transferring hole patterns. Lots of tools just for layout.
Incredible precision needed from the start. Okay, so you've measured, you've marked. Now you actually need to cut and shape the metal. There must be a whole arsenal of cutting tools.
Oh, yeah. Both powered for efficiency and hand tools for finesse. Let's start with power tools. Circular cutting saws are common high-speed rotating blade with teeth.
Handheld or table-mounted?
Both. Often air-powered in aircraft shops. Safety is huge with these obviously firm grip. Inspect the blade first.
Right. What else? Reciprocating saw.
Reciprocating saws, yeah.
Yeah.
Back and forth cutting action. They're versatile, good for tight spots, but maybe not the absolute cleanest cut. Different blades for different metals, of course.
Okay. And for really precise sheet metal cutting?
For cutting and squaring sheet metal accurately, you'd use a squaring shear. They have a stationary lower blade, moving upper blade, often have guides and scales for perfect 90-degree cuts.
But they have limits on thickness.
They do. Typically around 0.063 inches of aluminum for the foot-operated ones. Thicker stuff needs hydraulic or pneumatic shears.
Got it. What about curves and weird shapes?
For curves and irregular shapes, the throatless shear is amazing. It's called throatless because the design lets you rotate the metal freely as you cut. Really flexible for intricate shapes.
Cool. And cutting inside a sheet?
For that, you'd use scroll shears. They let you start a cut inside the metal without cutting in from the edge.
And punching holes, making washers.
That's the rotary punch press. Great for clean holes, rounded corners, even making custom washers.
What about smoothing things out afterwards?
For smoothing and polishing, you've got disc sanders and belt sanders. They use abrasive paper, different grits from coarse to fine. Often see combination units in shops.
Makes sense. And a notcher?
A notcher is for quickly and cleanly removing corners, usually precise 90-degree cuts. And then, of course, grinders.
Wet or dry?
Both. Essential for sharpening tools, shaping metal, getting smooth finishes. Again, safety is paramount. Goggles, check the wheels, adjust the rest properly. The source even details different abrasive wheel types, like silicon carbide for hard stuff, aluminum oxide for steel.
Okay, lots of power tools. But sometimes you need that hand control, right? What are the essential hand cutting tools?
For thinner sheet metal, your basic hand shears are straight snips. Good for straight cuts, gentle curves.
And for tighter curves?
That's where aviation snips come in. They're specifically designed for tighter curves, even circles, and they have that clever color coding on the handles.
Oh yeah, the colors. Yellow, green, red.
Right. Yellow is generally for straight cuts, green cuts, right-hand curves best, and red cuts, left-hand curves. Helps you work efficiently.
That's actually really useful. What else? Files.
Can't forget files. Crucial for shaping metal by carefully removing small amounts through abrasion. They come in all sorts of lengths, shapes, tooth patterns, fineness. whole science to files.
And after cutting, you get those sharp edges, burrs.
Exactly. That's where a burring tool comes in. Safely removes those sharp bits from edges and around holes, makes it safer to handle, and prepares it for joining.
Right, essential step. Okay, now let's move on to drilling holes. You said this is super common and critical.
Extremely common and absolutely critical. Making precise holes for rivets and bolts is fundamental. You'll see both portable power drills and stationary drill presses used.
Portable drills first. Pneumatic ones are common in shops.
Very common. Pneumatic drill motors are workhorses. Lightweight, powerful, good speed control. Most run around 3,000 RPM, but for harder materials like stainless steel or titanium, or drilling deeper holes, you'd want lower RPM, more torque.
Avoids damaging the bit or the metal.
Exactly. And for those tricky spots,
Ah, yeah, tight spaces.
there are right angle and 45-degree drill motors. And even specialized two-hole drills, specifically designed for installing nut plates quickly and accurately.
Nut plates, okay. And for maximum precision, the drill press.
For the highest accuracy, yes, the drill press is invaluable. Stable platform, precise positioning, good control over direction, and that feed lever gives you consistent pressure.
But what if you just can't get a straight shot, even with an angled drill?
Then you look at drill extensions and adapters. Extension drill bits are long and skinny, reach through small openings. Angle adapters attached to your drill chuck let you drill at, well, an angle.
And if even that doesn't work?
For the really awkward spots, there's even a flexible snake attachment. Lets you drill around obstructions. Pretty cool.
Wow, okay. What about the drill bits themselves? Step drills.
Step drill bits are neat. They drill a pilot hole and then enlarge it to the final size all in one go. Saves time, ensures alignment.
And different types of bits for different materials.
Oh yeah. High-speed steel, HSS, for general use. Cobalt vanadium for tougher stuff like CRES or titanium. And specific point grinds optimized for materials like aluminum versus titanium. Makes a big difference in cut quality and bit life.
And sizes. Numbers, letters, fractions.
All three systems are used to designate drill bit sizes. It's a whole range.
Do you need lubricant when drilling?
Interestingly, for most thin sheet metal drilling in aircraft repair, lubricant isn't typically needed. But for deeper holes, definitely yes. Keeps a bit cool, helps clear chips, prevents damage.
And you mentioned drill stops to prevent drilling too deep.
Right. Drill stops are simple collars you put on the bit. They limit how far it can penetrate, preventing damage to underlying structures or, yourself. Very important.
And keeping the drill straight.
Drill bushings and guides help with that. They ensure the drill bit stays perfectly perpendicular to the surface. Crucial for accurate holes, especially for critical fasteners. Now, getting those holes in precisely the right spot, that's key. How's that done?
It's a careful process. First, meticulous layout measure and mark the exact center with crossed lines. Then, use a sharp prick punch for a tiny indentation. Sometimes using a magnifying glass for extra precision.
Tiny mark first.
Right. Then, use a properly sharpened center punch to enlarge that mark. Creates a deeper divot that guides the drill bit tip, prevents skidding.
And the size of that center punch mark matters.
It does. Ideally, it should be about the width of the chisel edge at the very tip of the drill bit you're using. Guides it perfectly.
Okay, and after drilling, you get those little metal bits stuck between sheets. Chips.
Yeah, chips or swarf. That's where chip chasers come in. Thin, flexible tools designed to slide between the sheets and fish out that debris. Important for a clean joint.
Makes sense. Okay, so holes are drilled precisely. Now, often you need to shape the metal further, right? Forming, stretching and shrinking.
Exactly. Forming shapes the metal to fit perfectly, often using stretching and shrinking techniques.
Okay, let's talk about some of the larger machines first. Straight line forming.
There's the bar folder, used for making precise, straight bends and folds along an edge.
Simple bends.
Right. Then you have the press brake, much heavier duty for thicker, more complex parts, uses a punch and die combination to bend the metal to specific angles. Some are even computer-controlled for accuracy and repetition.
High production stuff.
Yeah.
And the box and pan brake.
Similar to a bar folder, but it lets you make bends of varying depths. Useful for making, well, boxes and enclosures.
Okay. What about rotary machines? For curves.
The slip roll former is key here. Creates cylinders and smooth curved surfaces by feeding metal between three adjustable rolls.
Rolling it into shape.
Exactly. And the rotary machine itself is versatile. Shapes edges, creates beads, other forming ops using various interchangeable shaped rolls. Usually works best on thinner annealed materials.
Annealed meaning softer, right?
Right, softer or more pliable, easier to work without cracking.
Okay. Beyond the big machines, there are smaller tools.
Lots of them. Piccolo former for small, intricate shapes. Shrinking and stretching tools for precise local manipulation. Form blocks, wood, or metal shapes you hammer against.
Shaping guides.
Yeah, and a whole array of specialized hammers and mallets, plastic, rawhide to shape without marring the surface.
And the source mentions some more advanced processes, stretch forming, drop hammer.
Right. Stretch forming involves stretching sheet metal over a shaped form block just past its elastic limit, creates a prominent shape with little spring back.
Okay.
Drop hammer forming uses impact force, often with matched dies. Good for design changes or short runs of complex parts.
And hydropress forming. Sounds interesting.
It uses a flexible rubber pad instead of a solid die. Presses sheet metal blanks over form blocks. Very versatile for making parts with flanges, beads, lightning holes, things like that.
Lots of ways to shape metal. Okay, so you know how to cut, drill, shape. But what metal are we talking about? You said mostly aluminum alloys, but it's not just any aluminum, is it?
Definitely not. The specific type is critical. Aluminum and its alloys are primary because they're light and strong. Pure aluminum has good corrosion resistance, good conductivity.
But it's not usually strong enough on its own for structure.
Right. So they combine aluminum with small amounts of other metals, copper, manganese, magnesium, to create alloys with very specific properties tailored for aircraft.
Tailored for specific jobs.
Exactly. And one important type you hear a lot about is alclad aluminum.
Alclad. It's the layered one.
Yeah, like a sandwich. A core of high-strength aluminum alloy covered on one or both sides by a thin layer of pure aluminum. That pure layer gives extra corrosion resistance, protecting the strong core.
Clever. So you get strength and protection.
Yep. And the source gets really specific about different alloys, like 1100.
1100 aluminum is used where high strength isn't needed, but weight savings and corrosion resistance are. Think fuel tanks, oil tanks, wingtips.
Okay, and 3003.
Similar, but a bit stronger and harder than 1100.
Then you get into the higher strength ones, 2014.
2014 is for heavy-duty forgings. Structural parts needing high strength and hardness, especially at higher temperatures.
And 2024, that sounds familiar.
2024, often alclad, is a real workhorse. Used widely for aircraft structures, rivets, heat-treated parts, skins, fittings, very common.
What about propellers?
Alloy 2025 is often used for propeller blades.
And 2219.
2219 is good for fuel tanks, structures needing high fracture toughness, weldability, and stress corrosion resistance.
Then there's the 5000 series, 5052.
5052 offers a good mix. Workability, corrosion resistance, fatigue strength, weldability, good for things like fuel and hydraulic lines.
And 5-diafix-6.
Often used for rivets, especially where aluminum might contact magnesium alloys.
It's amazing how specific these choices are, not just strength, but corrosion, temperature, fatigue.
Exactly. Each alloy is chosen for a very specific set of demands on that particular part. It really tells a story about the engineering involved.
It's like a whole specialized family of metals. But aluminum isn't the only player, right? Other metals are used.
That's right. While aluminum alloys dominate, other metals play key roles. Magnesium, titanium, and corrosion-resistant steel CRES.
Magnesium. Super light.
Incredibly lightweight, huge advantage, but big, but it's flammable. Requires very special handling precautions.
Okay. Titanium?
Exceptional strength-to-weight ratio. Holds strength at high temps. But it can be harder to machine, especially drilling. Needs specific techniques.
And CRES, stainless steel.
CRES, or stainless steel, is used for very high strength and corrosion resistance. But you have to be careful using it with other metals like aluminum or magnesium.
Why is that?
It can cause galvanic corrosion if they're in direct contact, so you often need protective finishes or insulators to separate them.
Got it. Materials prepped. How do you hold it all together? Rivets seem to be everywhere. Must be fundamental.
Riveting is absolutely fundamental. A very common, highly reliable way to permanently join metal parts in aircraft.
And lots of different kinds.
Oh yeah. Various alloys, head shape sizes, each designed for specific applications and stresses. A rivet that's perfect in one spot might be totally wrong for another. Understanding them and installing them right is crucial for integrity and safety. Speaks to that standardization you need in aviation.
And you can tell a lot just from the head markings. The source had that example. MS-20426 AD58.
Right. That code tells you everything. MS military standard, 20426 countersunk head shape, AD the alloy, 2117 T4 aluminum, 5 diameter, 532 inch, 8 length, 816 or 12 inch.
Wow, it's all packed in there.
It is. There are detailed charts showing all the styles and codes. It's part of that rigorous standardization, ensures the right part, right place every time.
How do you pick the right size rivet for a repair?
Size selection is critical. Generally, diameter relates to the total thickness of the materials being joined. A common rule of thumb, diameter should be at least 2.5 to 3 times the thickness of the thickest sheet.
Okay.
Typical range is 332 up to maybe 38-inch diameter. Smaller ones aren't usually used in primary structure. Often you look at nearby original rivets as a guide.
Or calculate based on skin thickness.
Yeah, another guideline is multiply skin thickness by 3, then use the next larger standard size.
And these little rivets handle big forces, shear and bearing again.
Primarily, yes. They resist shear the force trying to cut them in half, and bearing stress the pressure against the inside of the hole. A rivet can be in single shear, joining 2 sheets, or double shear, joining 3.
And you want that balance again between shear and bearing strength.
Exactly. Engineers design the joint so the total shear strength of the rivets roughly equals the total bearing strength of the sheet material around the holes. Ensures the whole joint is strong, no single weak point.
Makes sense. What about spacing? How far apart, how close to the edge? Are there rules?
Very specific guidelines. Always best to follow the original manufacturer's layout in that area if you can. The Structural Repair Manual, SRM, is the definitive source.
But if you don't have the SRM minimums?
Yeah, strict minimums. Edge distance center of hole to nearest edge must be at least 2 times the rivet diameter, ideally 2.5 to 4 times.
Okay, 2D minimum. And spacing between rivets. Pitch.
Pitch center to center in a row should be at least 3 times the diameter. And distance between parallel rows, at least 2.5 times the diameter. The source has good diagrams showing acceptable patterns.
Okay, rivets selected, locations marked. How do you actually install them? Tools, technique.
Proper installation needs specific tools and techniques. The pneumatic rivet gun is common, delivers rapid blows to form the shop head.
While the bucking bar holds the other end.
Right, a bucking bar, heavy, smooth metal held firmly against the factory head. Choosing the right rivet header for the gun is crucial, matches the factory head shape.
And the bucking bar matters too.
Absolutely. Right weight, smooth face matching the head held precisely 90 degrees to the shank. The person bucking needs firm, consistent pressure until it's fully formed.
What about hand riveting?
Hand rivet sets are also used sometimes. Handheld tool with a die, shape the head when struck with a hammer, and special draw sets can pull sheets tightly together before riveting to eliminate gaps.
Okay, now those flush rivets, the ones that sit smooth with the skin, how's that done?
For flush rivets, you need to create a countersunk recess in the outer skin so the head sits level. Usually done with a countersinking tool.
Different angles for different heads.
Exactly. Cutters match the rivet head angle. Microstop countersinks are often preferred. They give precise control over the depth for a perfect flush fit.
And dimpling, is that another way?
Dimpling is another method. Uses matched male and female dies to create a small indented shape in each sheet. The rivet head fits into these dimples, making a smooth surface. Often used on thinner sheets where countersinking might remove too much material.
Are there problems you can run into, like chattering?
Yeah, the source mentions potential issues. Chattering during countersinking can create a rough finish, and dimpling can sometimes cause tiny radial or circumferential cracks around the dimple, if not done correctly. Needs careful technique.
And after driving a flush rivet, sometimes you need to shave it.
If it's slightly proud, yes. A microshaver is a specialized tool that carefully shaves off tiny amounts of excess material for perfect flushness. But important note, shear head rivets should never be shaved.
Got it. Okay, installing rivets often sounds like a two-person job. Gunner and bucker, how do they coordinate?
Often with a simple tap code from the bucker. 1 tap might mean hit it again. 2 taps looks good. 3 taps stop. It's bad. Remove it. Simple signals.
Clever. What if you do need to remove a rivet? Bad install or for maintenance?
Several methods. Common way? Drill through the head with a slightly smaller bit than the shank. Once the head's off, punch out the remaining shank with a pin punch.
Or grinding, special cutters.
Yeah, grinding out the shop head is another way.
Yeah.
Or using specialized rivet cutters. Then punch out the shank.
Okay. Now, sometimes you can only get to one side of the structure, right? Blind rivets.
Exactly. Blind rivets are designed for those blind spots where you only have access from one side. But crucial point from the source for structural repairs on certified aircraft, using blind rivets needs specific authorization.
From the manufacturer's SRM or the FAA.
Right. Can't just substitute them freely. There are different types. Pull-through, mechanical lock, bulbed, each installed with a special pulling type rivet gun.
Okay. And it's not just rivets holding planes together. Other fasteners?
No, definitely not just rivets. Several other specialized fasteners are used. Pin fastening systems, sometimes called high shear pin rivets.
2 pieces, pin and collar.
Yep. A threaded pin and a collar that gets swaged or crimped onto the pin. Creates a very strong vibration-resistant joint. Installed with standard tools sometimes, but often need special gun sets for swaging the collar.
And specific types, high lug, high teague.
Exactly. High lug, high teague, high light, cherry bicky, all examples of high shear fasteners for specific high-stress applications.
What about lock bolts?
Lock bolts offer high shear strength and high clamp-up force. Used in heavily stressed areas. Need a pneumatic hammer or special pull gun. Come in pull type, stump type, blind type variations. Huck blind bolt is another high-strength blind system.
And drive nut types, Joe bolts.
Right. Drive nut blind bolts like Joe bolts, Visa Loki, Composi Loki, OSI bolt, Radio Loki. They use a nut, sleeve, draw bolt. The nut is driven to create the connection. Needs specialized installation tools.
That's complex.
They are specialized. The source also briefly mentions non-structural blind fasteners like pop rivets, but stresses they're not approved for primary structure on certified aircraft. Big difference.
Good distinction. Okay, we've covered joining metals thoroughly. Let's circle back to shaping it. We talked machines, but what about the finer points of forming in aircraft repair?
Forming metal accurately to fit those complex aircraft shapes is a real skill. Often involves stretching and shrinking the metal, and the hardness of the material is a huge factor.
Annealed metal is easier to work.
Much easier. Fully annealed metal, which is softened by heat treatment, is much easier to stretch, shrink, bend to smaller radii without cracking. Think soft clay versus hardened clay. Temper matters.
What are some common forming terms? Stretching, shrinking.
Stretching applies force to thin and lengthen an area, often creating a curve. Done with hammers, rollers, machines. Shrinking is the opposite, compressing an area to shorten or thicken it, also for curves or complex shapes.
And bumping, crimping.
Bumping is gently hammering malleable metal over a form or into a depression to gradually shape it. Crimping creates small folds or pleats to shorten or turn down a flange, and folding is just a sharp bend over on itself.
I remember hearing about bend allowance and setback for bending sheet metal.
Yeah.
What are those exactly?
Right. When you bend metal, the inside compresses, the outside stretches. Somewhere in the middle is the neutral line doesn't change length. Bend allowance is the length of that neutral axis within the bend.
Extra material needed for the bend itself.
Exactly. You need to account for it in your flat pattern, so the finished part is the right dimension after bending. Setback is the distance from the desired sharp corner mold line to where you position the metal in the break.
So these are key for accurate flat patterns.
Absolutely essential. The total developed width, TDW, is the overall flat pattern length, including bend allowances. The source shows how to calculate it, even using tools like J-charts to find bend deductions based on material, radius, angle. It also mentions closed end bends over 90 degrees need slightly different calculations.
Seems like a lot of math for a simple bend. What about hand forming without big machines?
Hand forming is a real craft. Still relies on stretching and shrinking, but with hand tools. Stretching might use hammers, levers. Shrinking can involve making small crimps, then compressing them with shrinking blocks and a hammer.
Or using a shrinking mallet.
Yeah, using a shrinking mallet directly on flanged angles is another technique. Forming a flanged angle often uses form blocks, wood, or metal guides, plus stretching or shrinking. Convex surfaces, like cowlings, are often formed by shrinking over a form block.
And bumping again, over form blocks or sandbags.
Right. Bumping is hammering over forms or sandbags to gradually stretch into shape. Sandbag bumping is really skillful. No rigid form, relies on feel and templates to check the shape.
And different metals behave differently during forming, right? Magnesium being flammable.
Absolutely critical point. The source highlights specifics for stainless steel, magnesium, titanium. Stainless steel needs larger bend radii due to its strength, prone to scratching.
Magnesium needs heat.
Often needs heating to form without cracking, as it's brittle cold. And that flammability requires extreme caution.
Titanium.
Titanium is strong, needs specific techniques to avoid work hardening becoming brittle as you shape it. Different bend radii, careful cutting pressures, specific drilling speeds. Each metal demands its own approach.
Okay, wow. Materials, tools, techniques. Now let's get to the heart of it, putting it back together after damage. The core principles of sheet metal repair.
Right. The number one goal is always restoring the damaged part to its original airworthy condition. Replacing the part entirely is often preferred, simplest if possible.
But when repair is the way to go. 3 main principles.
3 critical principles. Maintain original strength, maintain original contour, minimize weight.
Maintaining original strength seems obvious, but how do you actually ensure that?
It involves several key things. The source stresses ensuring the cross-sectional area of your patch or splice is at least equal to, preferably slightly greater than, the original damaged part's area. Carries the same load.
No weak links.
Exactly. Also, avoid sharp corners or abrupt changes in shape or thickness in the repair. Those create stress concentrations we talked about. Tapered splices, round or oval cutouts, help distribute stress smoothly.
Where you put the patch matters too. Inside or outside?
Generally, for parts under compression or bending, placing the reinforcing patch on the outside is preferred. If you have to put it inside, the source recommends using repair material 1 gauge thicker than the original to compensate.
And you can't just straighten bent parts.
Not if they're buckled or permanently bent structural members carrying significant loads. They should ideally be replaced or properly reinforced per approved procedures. Straightening weakens them.
And the repair material itself has to be similar.
Critically important. Use similar type and strength material. If you must substitute a weaker alloy, you must use a thicker gauge for equivalent strength. Can't just use thinner, stronger material. Other properties matter too, like buckling resistance. SRMs usually have material substitution tables.
And rivets again. Size, number.
Also critical for strength. Follow manufacturer's practice or guidelines in SRMs or FAA advisories. Interestingly, the source warns against making a repair too strong.
Really? How can it be too strong?
If it's significantly stronger or stiffer than the surrounding structure, it can cause excessive flexing and stress right at the edges of the repair. It can actually lead to fatigue cracking around the super strong patch. Balance is key.
Okay. Maintaining original contour, that's about aerodynamics.
Precisely. Keeping the original shape and smoothness is crucial for performance, stability, fuel efficiency. Repairs need to blend seamlessly. No bulges, depressions, sharp edges disrupting airflow.
And minimizing weight, back to that core aircraft design principle.
Exactly. Avoid unnecessary weight. Every extra ounce impacts performance, fuel burn, payload. Keep it light but strong.
The source also mentioned balancing shear and bearing strength again in joint design, aiming for that sweet spot.
That's a good way to put it. You want to design the joint, select the right number, size, material of fastener so it's balanced. Not significantly weaker in shear, fasteners breaking, than in bearing, sheet tearing at holes, or vice versa. Makes the whole jet reliable.
And something I wouldn't have thought of, aircraft balance and center of gravity. Repairs can affect that.
Definitely. Especially on lighter parts like control surfaces, rudders, elevators, ailerons. Even small weight changes there can affect balance, potentially leading to flutter.
Flutter, that dangerous vibration.
Exactly. So repairs on control surfaces must maintain original weight distribution very closely. If there are counterweights, they're only adjusted per manufacturer instructions. Sometimes a test flight is needed post-repair to check for flutter.
And the ultimate guide for any specific repair is always the manufacturer's SRM.
Always the primary resource. Manufacturers put huge effort into developing specific, detailed procedures for their aircraft models. SRMs have illustrations, material specs, rivet details, step-by-step methods. If the SRM doesn't cover your exact damage, look for similar repairs the manufacturer has outlined.
Okay. Now, before fixing, you have to find the problem. Spotting damage, defects, inspection.
Regular, thorough inspection is absolutely essential. Look for telltale signs. Panels bent, buckled, wrinkled, loose or working rivets.
Working rivets. They might not look loose.
Right. They move slightly under stress, sometimes indicated by dark, greasy residue or paint cracking around the head. These often point to bigger underlying issues.
And the source listed a whole vocabulary of damage types. Brunelling, corrosion, cracks.
It did. Understanding terms like crack, physical separation, dent, indentation, corrosion, chemical degradation, galling, friction damage, is key to accurately describing the damage. Each type has different implications for repair.
And damage gets classified. Negligible, patchable, needs insertion, needs replacement.
That classification helps decide the action. Negligible is minor surface stuff, monitor it. Patching reinforces with splice members. Insertion replaces a damaged section. And sometimes damage is too severe or the part too critical replacement is the only safe option.
So thorough assessment is step one, always.
Absolutely. Evaluate the extent, nature of damage. Is repair even authorized? What's the right procedure? Identify original materials. Inspect surrounding areas, joints for hidden damage, corrosion.
You mentioned smoking rivets.
Yeah, that's a term for dark residue around a rivet head.
Mm-hmm.
Indicates significant stress, possible underlying issues. Needs investigation. There are also limits for acceptable cracking in rivet heads themselves.
And checking for corrosion inside and out.
Crucial, especially internal areas around drain holes where moisture collects. Hidden corrosion is a major concern.
Okay, damage assessed. What are the general repair steps?
Damage removal. First, Carefully remove all distorted or weakened material. Ensure remaining edges are sound, aligned properly. Round any sharp corners in the cutout, minimize stress risers. Smooth out nearby abrasions or dents. Remove any old repairs in the area.
Material selection. Match strength.
Must duplicate original strength. If using a weaker alloy, compensate with thicker gauge. Never use lighter gauge, even if stronger alloy, without engineering approval.
Layout. Follow the manual.
Carefully lay out parts per SRM dimensions. Precision matters.
Rivet selection. Original size usually.
Normally, yes. Same size, type, material. If holes are enlarged, might need next larger size, but must maintain proper edge distance. For blind rivets, consult the manual for approved type, size, spacing, number.
Rivet pattern. Match original.
Follow manual guidelines. Match existing pattern in undamaged areas whenever possible.
And treat corrosion before assembly. Insulate dissimilar metals.
Essential steps. Treat existing corrosion. Use proper insulation between dissimilar metals to prevent future galvanic corrosion.
And any significant repair needs official approval, right? Can't just DIY it.
Absolutely correct. Regulations like 14 CFR Part 43.13a require maintenance to use methods acceptable to the FAA. Primary sources, SRM, FAA advisory circulars, other FAA-approved data.
And major repairs need special paperwork, Form 337.
Typically, yes. Major repairs, primary structure, material substitutions, significant skin damage require FAA Form 337, documenting the repair and data used. Needs approval from FAA or a DER. Certified repair stations might use work orders sometimes, but still need approved data.
The source even gave an example of designing a patch for a non-pressurized area. Seemed very systematic.
It is. Examples showed removing damage, shaping the cutout. Round oval rectangle with rounded corners avoid stress risers.
Right.
Determining edge distance spacing, selecting doubler insert material, often doubler is 1 gauge heavier, choosing rivet type size based on similar joints or SRM. Very methodical.
And finally, those examples of typical repairs, floats, skin, stringers, bulkheads, spars, really helps visualize it.
Those examples are great. They show applying principles in real situations, replacing panels, splicing stringers, reinforcing cracks in bulkhead spars with doublers, specific rivet patterns. Even reinforcing access holes needs specific SRM procedures. Always stresses, consult the specific SRM for that aircraft.
Well, that was a truly deep dive, incredible detail in aircraft metal repair. So much more than just patching dents.
It really is.
Yeah.
What's striking is how interconnected it all is, isn't it? Design, stresses, material selection, meticulous repair techniques, everything has to work together.
Yeah.
Even making a repair too strong, creating those stress risers,
Yeah.
it shows the complexity. And little details, like the colored handles on snips having a real function, underscores the engineering thought involved.
Exactly. And considering all of this, it makes you think about repairing, say, a vintage aircraft, different materials, older design philosophies, and how do you apply these modern principles then? Whole other challenge.
Precisely. This deep dive, hopefully, gives listeners a much deeper appreciation for the engineering, the standards, the meticulous maintenance behind aircraft safety and performance. It's not simple stuff.
Right. It takes deep understanding and skill. So for you listening, maybe think about how these principles, understanding stress, material integrity, following precise procedures might apply in your own world. Machinery, construction, even big DIY projects.
You might see parallels.
Yeah. And if this sparked questions or insights, we'd love to hear them.
Ultimately, what we've explored today just highlights that even in what seems like basic metalwork, there's this profound level of knowledge, skill, and unwavering attention to detail needed, especially when safety is paramount, like in aircraft.